So this is really one of my favorite topics I like to talk about. And so basically, I spent the last 6-7 years on this topic of future indoor networks, and I have the subtitle, it's with a sixth sense. And in those years, and I think the vision for what future indoor networks will be in the future has shaped up, and I'm sharing this today. And thanks, Sajal, for introducing me already, so I don't need to say much about myself. Maybe one thing I want to add to this, on the 1st of January, actually, I started in a new position, so I changed to the business line, to Nokia Technologies, and I'm there the chief architect for IoT, which is, of course, closely related to what I talk here. And so without further ado, I want to introduce the organization where I come from. So this is Nokia Bell Labs, and just want to remind people, this is really, I think, the organization which many model their breakthrough, their moonshot innovations after our organization, after Bell Labs. So a lot of groundbreaking research was done there, Nobel Prizes, Turing Prizes, and so on. So that also got a lot of recognition in many fields. So all of them more or less communications related. And we still have that DNA in our organization. And today I think everybody talks about 5G, so it's really one, even our president, the former and also the current president will be realizing that 5G is really one of the core technologies that enables us to step into the future. And Nokia has, of course, Bell Labs has been a pioneer in 5G technology. And so this is like, release 15, 16, and 17 of 3GPP. So it continues to evolve, and already now we have started the research on 6G. So this is really, we are one of the top 5 players in this space. And to all the students, I think it's not a surprise that I will tell you this, but watch out for what's going on in that field and the developments there. It will really change the way the society works, and especially during this pandemic, we already realized how important mobile communication, broadband internet, access to internet is for the countries at large to be able to deal with such a pandemic. And yep, I think I have one more slide on this before I move on. So just to give you a glimpse about the scale of our research. So we had about 3,000 essential patents inside the 5G technology, and I think we are approaching more like 4,000 this year. Nokia and the companies we acquired have invested 129 billion euros in R&D in the last 2 decades. And just last year, we have filed 1,300 new patents. So this is really just to give you a little bit of an idea about the scale of the operation. And also, it gives you some sense on how complex actually it is to make a wireless, end-to-end wireless system that works like 5G is working. So, and with that, I want to dive now into the topic that I want to talk about today, so the future indoor networks with a sixth sense. And of course, when we talk about networks, connectivity is the most important thing. Nobody plugs anymore the Ethernet cable into the laptop, so everybody is connecting wirelessly. And I think that indoor networks are still very much dominated by Wi-Fi. So today I'm actually not talking about 5G, but I'm talking more about Wi-Fi, what's happening there, and introduce Wi-Fi 6E, and why that is actually a big deal. And then I have also a comparison that we did, and I think it's one of the few kind of neutral comparisons between Wi-Fi and 5G. So this was done by our researchers in system simulations, and it was done by the Wi-Fi research team and the 5G research team. And it was really, at least from my perspective, what I've seen so far, that white paper that we have published is one of the most objective ones you can find today. And then from the connectivity part, I go to the sixth sense. So I will talk a bit about localization, sensing, and finally I will end this talk with the vision of where this all will lead to. And this is a concept that we created in Bell Labs, which is called MirrorX. So this is really the furthest into the future that I will talk about today. Good. And with that, so just to give you a very brief introduction. So, I talked already about that Wi-Fi is the dominant indoor networking technology. My prediction is that we will see that in residential, in enterprise. We will see Wi-Fi in places where capacity is important and cost efficiency. And then on the other hand, we have 5G and 6G, so which will come up. The research just has started, and there I see that 5G makes a strong push into industrial applications. Of course, 5G provides also a lot of capacity, and in addition to capacity, also coverage. So in places where coverage reliability is important, 5G is going to be more and more the technology of choice, and especially if you need reliable low latency. And this is like, something that a conclusion that you can already take away from this talk. I will go into more details on showing you some of the results that we have that support this. But first, I really want to go to Wi-Fi and what's going on there. And I think you all have heard about Wi-Fi 6. So this is like everybody talks about it. We see new routers entering. We hear companies talking about how Wi-Fi is the new 5G technology. It can provide so much capacity. And just last year, there is a new part of the spectrum that the FCC has opened up. So that's in the 6 gigahertz band. So we have now 1.2 gigahertz of spectrum for Wi-Fi technology, or for unlicensed technology, so not just Wi-Fi, of course. And this 1.2 gigahertz, that, for example, corresponds to 760 megahertz channels. So this is huge capacity that we have there. And it's also, we have already the technology to deploy it there. So already in this quarter, we will see that the certification program starts from Wi-Fi Alliance. And just to give you one more takeaway message is in addition to having a huge amount of spectrum now available, this spectrum comes without legacy from old technologies. So no Wi-Fi 4, which is .11n, or Wi-Fi 5, which is .11ac in that band. And I will show you a bit later why that is actually a big deal. And what do we use this for? So Wi-Fi Alliance, for example, states use cases like mixed reality in buildings, so multi-dwelling units, where you need a lot of capacity, wireless offices. And my favorite vision really is that just imagine instead of having all these cubicle farms, people could go to their cubicle, they have their mixed reality environment, and everybody basically has the feeling to be in the corner office. And we did some estimates with a lot of clever tricks that would require about 100 megabits per second for each of those cubicles, for each of those spaces. And that means that if you have 200 people on the floor, that's a huge amount of data, 20 gigabits per second, that you need to provide to those workspaces, and you need to do that with low latency. And this is really the kind of capacities that we see the Wi-Fi technology evolving to be able to provide. So that is the use cases. There is, of course, whenever we get new spectrum, it's really important to look at the fine print. So what are the kind of regulation that you have there? And the key message I want to bring you there is that currently so basically Wi-Fi 6E can operate indoors. And just to basically point out, for example, there is always a restriction on the transmit power. So what is the maximum transmit power that you can use? And this is 30 dBm. That's pretty much what you can use also in the 5 gigahertz band. But the difference now is that spectrum, you can only use the transmit power of 30 dBm if you have the whole bandwidth. So if you have the 160 megahertz. When you basically want to increase coverage, you can basically reduce the bandwidth and increase the coverage. But with Wi-Fi 6E, we cannot do that because we are restricted by the power spectral density. And if we reduce, for example, the bandwidth to 20 megahertz, then all we can use is 18 dBm, so 12 dB less at the access point transmit power. And this is something that I just want to basically state here. That is a really big disadvantage because that reduces the coverage that you will get. And this is, later on I have a comparison between Wi-Fi and 5G, and we will see what, how big the difference really is. And then there's also a second mode, which is outdoors, where you actually need to access a database to be permitted to transmit. Kind of comparable what you see in the CBRS band, the 3.5 gigahertz band. And that is actually not yet operational. So that database system doesn't exist yet for the 6 gigahertz band. So what we see now is actually the indoor-only devices coming to the market. So that is, if you're interested, I have a link here also from FCC where you can read about more about the regulation. So it's if you want to dive deeper. And now just to remind you a little bit, what are the key features of Wi-Fi 6? And I think the one key feature is really that Wi-Fi 6 is also an OFDMA-based system. So similar to 4G, similar to 5G, we have now OFDMA, we have a scheduler, and that makes the system much more deterministic. So Wi-Fi is getting actually much closer in how it operates to 4G, 5G systems, but there is still some differences there. The second thing is that it actually has a better support for IoT. So, for example, Wi-Fi 5 AC was not defined for the 2.4 gigahertz band. And a lot of the IoT devices that need to run on low power, that still want to have a decent coverage, they basically operate in the 2.4 gigahertz band. And those devices were still all operating on .11n. So now, Wi-Fi 4. And so now with this Wi-Fi 6, we see that all this, or most of these low power devices, that they are going now into AX, into Wi-Fi 6. And of course, with every new generation, a lot more capacity, so multi-user MIMO, 1024 QAM, and so on. So the peak throughput has increased as well. And just a reminder, OFDM versus OFDMA. So with OFDM, I basically have the whole bandwidth allocated to each of the users when they transmit. And then with Wi-Fi, I have this channel access procedure. So in the unlicensed band, CSMA, CA, carrier sensing and collision avoidance. And basically, I get a lot of gaps. And especially if I have to transmit like small amount of information, mostly I have gaps in my spectrum. But then with OFDMA, I can basically pack together the downlink transmissions and the uplink transmissions. I can schedule them so I can provide much better fairness than a statistical channel access scheme can provide. And so I can use the spectrum way more efficiently. But what we currently have when we put Wi-Fi 6 in the 5 gigahertz band, we still have those Wi-Fi 5 devices that operate with OFDM. And we still have the Wi-Fi 4 devices. And sometimes even worse, we have .11a devices still, and so on. So now I will never see the full benefits of Wi-Fi 6 if I have those legacy devices present. Because if I want to provide low latency services, if there's a legacy device taking up, for example, 5 milliseconds of the spectrum in a transmission opportunity, I have to wait until that guy is ready until I can transmit. So that means that I can never get deterministically low latency. And this is really one of the key disadvantages that I have currently with Wi-Fi 6 until all those old legacy devices are out from the spectrum, and that will take maybe 10 years or so. And with Wi-Fi 6E, so there is the decision that I actually do not have those legacy devices. So there will not be a Wi-Fi 5 in the 6 gigahertz band. So the only one that goes in the 6 gigahertz band is Wi-Fi 6. And so I actually avoid all these disadvantages from having legacy present. So this is really where the Wi-Fi ecosystem can get the full benefits from this new technology in the 6 gigahertz band. So that is, I think, one of the key things. Wi-Fi 6 has OFDMA. And the second thing is that there is, with Wi-Fi 6E, there is no legacy present. So I will see the full benefits from this new Wi-Fi 6 technology. So next, I want to now start to look at, so how does Wi-Fi compare to 5G? And the first one I already mentioned is talking about coverage. So that is really one of the key advantages that we have with cellular technology. And for example, if we look at indoor spaces, if I have a 5G licensed band available, so CBRS, for example, I can get with 5G with the transmit power that I'm allowed to use, and with the way the system is designed and the devices are implemented, I get a cell range of, for example, 300 meters in downlink and 200 something meters in uplink. If I look at Wi-Fi now in the 5 gigahertz band, so this is basically, I get a bit more than 100 meter cell range in downlink, and I get around 50 meters in uplink. And this is, if you think about this in terms of area, that's of course a huge difference between the two technologies. And so this is, and then there's of course a variant of 5G also in the unlicensed band, and that variant is somewhere in the middle between the licensed 5G technology in a licensed band and Wi-Fi. And later on, we will also do a bit more comparison between 5G unlicensed versus Wi-Fi. But the key takeaway here is that Wi-Fi is more designed for capacity, for low-cost devices, so cost-efficient implementations. And the main difference you see compared to 5G is in the coverage of when you compare those two technologies. Good. And then the next one is looking at low latency traffic. So I mentioned in the beginning that with 5G, we will see it more and more in industrial applications where we need capacity, where we need coverage, and where we need reliable low latency. And here, I think that's an interesting chart. There is two takeaways for me here. So this is basically looking at the low load situation, let's say 10, 20% channel occupancy. What is the kind of latency that we see of the packages when we receive them? And this is for different reliability requirements. So how long does it take to get 99% of the packages, 99.9%, 99.99%, and the dark blue one here is basically how long does it take to get 5 nines of reliability. And what we see is that with 5G in unlicensed, for example, in a low load situation, it's less than 10 milliseconds to get 5 nines of the packets successfully received. And if we look there at Wi-Fi 6, we cannot provide 5 nines of reliability. But the interesting part is here in a low load situation, sorry, Wi-Fi 6 has actually up until 4 nines slightly lower latency than 5G. So, but then it cannot provide this 5 nines of reliability. That's where Wi-Fi 6 will fail. And then if we look at basically 5G in unlicensed versus Wi-Fi in high load scenarios, so there we see that 5G in unlicensed is still able to provide this 5 nines of reliability. And actually now the latency in a high load scenario is always less than what we get with Wi-Fi 6. So even though Wi-Fi 6 has made a lot of improvements for Wi-Fi technology to basically provide something like deterministic low latency with scheduling, OFDMA, and so on, when it comes to 5 nines, it is not able to do that. And in high load situations, you can see that 5G is just a much more efficient radio system. So basically, that's when 5G will outperform Wi-Fi. And here in the bottom, there's actually a link to a white paper that we have done where we summarize all this basically comparison between Wi-Fi and 5G for indoor networks. And I don't go through this whole table here, so I invite you to read that white paper, but just a few areas that we have mentioned already. So this is like when you look at coverage, we have about 20 times the area when we look at 4G and 5G in licensed bands. And it's about 4 times the area when we look at 5G in unlicensed band compared to Wi-Fi. That's the coverage. When we talk about latency, so this is like, especially when we come to high load, and then the latency will be better in 5G. And in Wi-Fi 6, we say here it's partly load dependent what the latency is. Then if we talk about ultra-reliable low latency communication, so this is also something where 5G really makes a difference, is very much ahead of Wi-Fi. There is some proprietary features that you can do with Wi-Fi to improve the latency, but in general, 5G has been designed for ultra-reliable low latency, whereas Wi-Fi has not been designed for that. The next area is actually, that's why this smiley is in the middle here between those two lines, is when we talk about mobility. So this is, of course, especially 5G has really been designed for mobility. So it has been designed for high-speed trains that run at 500 kilometers per hour, and it can do successful handovers in such situations without breaking the connection. And of course, if we look at indoor with pedestrian speeds and so on, or fairly low speeds, it really works well. So meaning that you can roam through the network, you have successful handovers, all of it is coming from the network. You get a very high reliability for your mobile devices, for your autonomous vehicles and so on. And with 5G, you can really start talking about putting even critical functions of, for example, autonomous robot into the cloud, implement it there, use all the computing power and the ability to, for example, update the computing hardware over time. You can really make use of the cloud there. Whereas with Wi-Fi, the handovers are still not really at this level. And especially, we do quite a bit of research with autonomous robots. If you, for example, take some Linux operating system and use that network managers there, typically you get things like sticky clients that do not hand over. You lose your video connection, for example, to the cloud. And it's extremely difficult actually to get Wi-Fi to do successful handovers in such situations in an industrial scenario. So there is really like, don't just look at the static cases, but we all want to move around. We have autonomous vehicles, people, devices, assets that move. And there also 5G, of course, has been designed for mobility. But of course, it's like we will see a lot of innovation on Wi-Fi, and the main reason is that it is actually much lower cost than 5G. And the devices are cheaper, and there is a huge ecosystem, and I think we will see Wi-Fi growing and growing in terms of use cases. And quite many of those problems that we see today with Wi-Fi for reliable low latency will be somewhat lower and more use cases can be implemented, but the industrial ones where you really need this reliability, and that's, I think, where we will see 5G way more than Wi-Fi. And I personally believe some of those things cannot be done with Wi-Fi. Good. So that is the connectivity part. I think that's super excited. What I expect is that with these technologies, we are actually equipped to provide ubiquitous gigabit connectivity indoors, and both in residential, enterprise, and also industrial areas. So now from this connectivity part, I want to go to the next part, which is actually connectivity. I still have 2 slides for that. Where is the Wi-Fi ecosystem going? So there's Wi-Fi 7 standardization just ongoing. We will again increase the peak rates, so we get more than 30 gigabits per second peak throughput. We also will see further development in reducing the latency and the jitter. So for example, integrating Wi-Fi with time-sensitive networking in IEEE. And Nokia Bell Labs has actually been pretty active in the Wi-Fi 7 standardization. And for example, here we have done some evaluation of comparing Wi-Fi 6 to Wi-Fi 7. And what we can see is really that we expect that we get 3 times the throughput in the medium term, but even more improvements in the lower percentiles in the station throughput. So this is where connectivity is going. And then, of course, with 5G, we will go into 6G, which will further improve the system. And every new generation provides a lot of more capacity as well. But now I want to go into something different. So this is like the vision that we have is we have gigabit connectivity everywhere. Today, I have a fiber to my home. I pay $60 a month, and I get the gigabit per second to my home. So I want to see that all through my house. And the way I do that is in a residential space, I put up a Wi-Fi mesh network, and I actually needed to put 1 cable between the 2 floors so that I can really distribute that capacity inside the house, because the 5 gigahertz band did not penetrate the floors, and I didn't see that, let's say, my minimum requirement is 300 megabits per second. I didn't see that in the whole house, so I needed that 1 cable connection still. But in enterprise spaces, I did look at our new office space in Sunnyvale, and I think I would say every 15 meters, every, let's say, 50 feet, we have an access point inside the building. And that is actually something interesting, because when you have this many access points, we started thinking is like, why don't we use that for other stuff as well? Because, you know, we talk about smart buildings, smart enterprises, all of that needs a lot of sensors. So this is where we actually then said is like, there is actually a symbiosis of connectivity and sensing. So we have all those access points, which can be also sensor points. So let's use that. And there is a paper that we are just publishing. So it's called Future Indoor Networks with a Sixth Sense, Requirements, Challenges, and Enabling Technologies. So that will appear in the Bell Labs Technical Journal, should be actually this month or latest next month. So some of the results that I have in there and some of the content is actually a little bit of a teaser for that paper. And so the obvious thing is, of course, that we can add all the sensors to the access point, but how about the radio itself? What can we do with that? And the first thing what we can do is that, of course, every device that is connected to our system, we can try to localize where is that device. And there is basically in RF-based localization, there is 2 techniques. So one is based on time of arrival. So that means that, for example, if I have a transmitter here, I have 3 access points that receive the signal. Assuming that they are perfectly synchronized, I can basically calculate, for example, the time difference of arrival between them, and I can triangulate the position of that device. Or I can do ranging to 3 access points. So I measure the distance, I can triangulate the device, and so on. So basically, based on time information, I can determine the location of the transmitter. And the same thing I can do also, we see that, of course, with all the new MIMO and whatever capabilities, I can look at the angle of arrival as well. So I have a lot of antennas, I can calculate the angle of arrival. If I have 2 access points, I can just triangulate there again, and the intersection gives me the position of the sender, of the transmitter of the signal. Of course, this works perfectly in line of sight. When we go to real world situations, I have obstructions, I have multipaths that are sometimes unresolvable, so I need to go to higher bandwidths to basically be able to resolve the multipaths. So we did some theoretical studies. So once I go beyond 80 megahertz, I start to see in a normal indoor environment where you have the access points above the clutter and so on, I see that at above 80, 100 megahertz, I actually, the channel opens up, I can resolve the multipaths. So that is, with the multipath, we actually have the chance to use higher bandwidth, and that helps us there. But then we also have the non-line of sight reflections. So this is, these methods assume that you have multiple access points in line of sight, and just imagine the cost of a deployment where I have always 3 access points in line of sight. So we have a system that is basically very good at doing localization, but it still relies on a lot on having those access points in line of sight. Then, of course, you have to basically look at the signal coming in from, let's say, the 20 closest access points that receive the signal, and you have to decide which ones of those are actually in line of sight, where the angle, where the time of arrival is actually the right one, and it's not going through a non-line of sight reflection and so on. So the reality is actually really hard to do accurate, precise localization, especially when you go to a complex industrial environment. So this is the high accuracy positioning in real environments is very, very difficult. But I just show you some results that we have with our indoor positioning system. And this is basically, we deployed it in Murray Hill in New Jersey in our headquarters of Nokia Bell Labs. And so basically it's installed in a single floor, and that floor has open spaces, it has hallways, it has offices, it has transitions. So it's actually a pretty challenging space for an indoor positioning system. And we have built that system actually because we wanted to have very cheap, low-cost devices. So we use Bluetooth Low Energy, and we have locators that have an antenna array in there. And those locators actually use the constant tone extension of Bluetooth Low Energy. And our badges, they just transmit the signal, and then the locators switch between the antennas. So we get effectively a 14 antenna array. We can estimate the angle of arrival, and then we have a lot of intelligence to kind of deal with non-line of sight reflections and so on to basically, and then have Kalman filtering on top and so on to basically track the location of those tags. And here you can see the results of a trajectory that we took. It was 243 meters. And I think it's pretty impressive. We get a median error of about 30 centimeters. And much more important, the 99th percentile of the error is 1 meter. So for 99% of the cases, we have better than a meter accuracy. And that also means that you get into an area where you can start to really deploy location-based services because you can be pretty confident that your location is correct. And where is this going? So what's next within this space? So there is also quite a bit of activity in Wi-Fi localization for years and years now, actually. There is also, we are active in 5G localization. So release 16 starts to actually specify some of enhancements to allow localization to support it better. So broadband localization, we see more of that because that was also one of our realization is, if I have a 5G connected ground vehicle, why do I use the narrowband radio for positioning? So we should actually use the radio system we have, the most capable one for the localization. And then we have also started to do the combination of angle of arrival and time of arrival. And if you have a standard that allows you to do very accurate ranging, so distance measurement, then you can actually, just with having the angle and the distance, you can actually already estimate the position. So you just need to have one of the locators in line of sight. And then, of course, the one thing is that we need to reduce infrastructure costs. So the requirement of just having one locator in line of sight is already pretty good because that reduces our costs to deploy the infrastructure. But the second thing is really how to deal with non-line of sight reflections. And, we see that there is some research, which is, I'm really curious how that is going, to see, to model the environment, to find the dominant reflectors, and basically to, based on that, reconstruct the path that the signal takes, and to be able to actually calculate out the effect of non-line of sight reflections. But I think it's really promising to do it with the help of machine learning. And we saw some interesting results there. And I think we will see many more in this space. And as with all machine learning parts, is the challenge really is to get a good ground truth data, a good training set. And there, I think we will also benefit from the fact that, especially in industrial environments, we have a lot of ground robots, drones, and so on. Many of them will have LiDAR as their positioning system. So we can draw from the ground truth that we get from those robots and train our system so that also then when other devices that do not have a LiDAR come into the space, drive around, or people, assets, tracking that with high accuracy, we have the machine learning system to basically be able to do that and to deal with the non-line of sight situations. But of course, there is limitations to that because the environment is changing, and especially we are interested in this 99th percentile. So today I'm seeing promising results, but I'm not sure machine learning will actually get us there. And I think that's the end of where I am with localization. And this is, of course, many more things, assets, devices will be connected that we are interested in our smart buildings, enterprises, factories. So localization, where things are, to know that with high precision is a key ingredient. Next, we were also looking at, I think you're all familiar with the principle of radar, and there is two different concepts. One is basically I have a transmitter, and I send out the signal, I receive the return, and basically I can determine motion reflections that I see with the signal. I think everybody knows that concept. There's also another form of radar. It's basically called bistatic or multistatic radar. So I have a transmitter here, I have a receiver here, and in between, that signal gets reflected somewhere, and I see the movement, I see the reflections at the receiver. And if I know the location of the transmitter and the receiver, I can get a lot of information out of there. So it's very natural that we start to think about using the RF also as an activity sensor. And of course, with the advent of machine learning, we saw a lot of activity there. So this is like, there are papers where you use, let's say you have a laptop, you have a Wi-Fi receiver and an access point. You can get access to the channel state information because every movement perturbs the channel, so you can see those movements in the channel. And as long as I have exactly the same setup, the same person sitting there, I can even sense what a person is typing on the keyboard with a pretty good accuracy. Of course, these systems are not very robust. So if there's a different person sitting there, or the person is not sitting at exactly the same spot, the models that I train there are basically useless. And so it kind of shows you that what kind of information is actually in that received signal. And especially when we look at this, it's pretty standard now that we have 4 antennas in our access points with Wi-Fi 6. We see already 8 antenna access points being pretty commonplace and so on. So naturally, we wanted to also look at what can we do with machine learning. Can we classify activities? Can we determine the location of a person, for example, even if the person does not carry a smartphone, and so on? Because if we want to really build services that benefit people, knowing their location is important. And just, for example, your Google Home, your Alexa, they are actually still pretty dumb in a sense that I need to say, hey, Google, okay, Google, turn up the living room lights. And I need to say that because my Google Home client doesn't really know where I am. And of course, they try to infer it with noises, with sounds that they can basically sense, but it's not accurate enough that they can really rely on that. And so, to make these voice interfaces more intuitive, to automate more and more in my smart home, knowing the location and what the person is doing is actually a pretty interesting information and enables a lot of things. So that's why we looked at this more from a residential perspective, actually. And on the right-hand side, you can see a plot. So this is the 5 seconds of the signal that we receive from 4 antennas. And you can see all those variations that we can see in the channel state information. And we tested this as a motion sensor. So this is actually a pretty complex, it's our model home, so that Nokia has a pretty nice home Wi-Fi system that I use in my house. So that's where I get my 300 megabits throughout the house. And in the development, a lot of that is happening in Shanghai, in China. And so this is a setup that we have there. So we have one access point here that is serving the house. We have a few stations. 2 of them are actually TVs, so in the living room and the bedroom. And I don't recall what we had in the lobby. And basically, we were using those devices to sense. So we were using those devices as transmitters, and we had the access point with our Wi-Fi 6 chipset in there. The access and recorded the signal there, recorded the variations in the channel state information. We used some of the data to train the system based on where the location is, and then we used the rest of the data then to verify, how accurate our system is. And I think that the unique part of this research that we did there is, first of all, that we used cameras to determine the ground truth of the location. So that allowed us to actually do a lot of data collection. And we had, I think it was more than 10, maybe 20 different people there moving around in the space. We did that for several hours. So in the verification data, not just did we just use part of it, but we also had people in the system that we haven't seen before. And what we can see is that it's actually, I think if you look at the layout of this building, it's pretty complex. And we modeled the real life situations where you don't have the stations at all the correct locations. But still we can see that with about 80 to 90%, we can actually get the room where the person is correctly estimated with our machine learning system. So it's kind of, if you combine that with other sensors, with other inputs, I think we can reach a state where we can pretty accurately determine the location of a person in a house with using machine learning. And again, in this case, people were not carrying a smartphone. So this was just people moving around, no smartphone connected. Good. So that's using Wi-Fi as a sensor, and especially for location, I think that's for large motions, it works pretty well. Beyond what we are doing in the RF sensing space, so I think the important part is really that you start fusing the inputs. So especially in enterprise industrial areas, you have a lot of cameras in the space. So you should also use that as a sensor. You can have environmental sensors and motion sensors. So either based on our own RF signal, or just put the dedicated motion sensor in there, an accelerometer, and so on. So I think these sensors are very low cost today and would add a lot of information. And with the density of Wi-Fi access points of communication, maybe later on 5G in industrial environments, access points, we actually have the density of sensors there that really help us to power our smart homes, smart buildings, smart enterprises. And then this is then the realization that I arrived at is infrastructure sensors can't just get you that far. There's always obstructions. There's always parts that are hidden from you. You cannot put sensors every 2 meters to basically circumvent that. So there will be really important is to also combine this with mobile sensors. So for example, I can send an autonomous robot, a drone, into areas where I want to know more. Let's say I detected something that looks suspicious, I can send a robot, a drone there. Much better than relying on having infrastructure every 2 meters. The second thing is that we'll see that, of course, we already run around with smartphones that are powerful sensors. But in the future, we will actually run around with mixed reality devices. So we will have those things on our head, most likely, maybe glasses, that allow us to sense the environment. And not just sense it, like create a spatial model of the environment. And so we should benefit from that here as well. So our workers, for example, in a factory, could contribute to such a system. And of course, the most powerful sensor that we know today, and a lot of the machine learning is done in that space, is cameras. So, and I have cameras on everything, on the mixed reality devices, on the autonomous robots, the drones. And, if we are able to fuse all of that information together, so if not each of those device categories create their own silo, but we are actually able to fuse it together, I think this will become the ultimate platform that we can work with. So it allows innovation that we haven't seen yet and which we don't even understand what this unleashes. So it's very exciting. I'm really looking forward to what's going on there. And so where we have started here is using the multisensory system, and in this case, not yet fusing all of this information together, but we have realized that it's extremely hard to collect that training data, with which you can basically collect RF signals, a large amount, train the system, and then you use it for machine learning and classification. So you need millions and millions of data points to kind of get a machine learning network, a network that is kind of generalizing. So you need to do this automated. You cannot really do that with manual labeling, whatever you're trying to do. And so we have developed our own system that is basically camera-based, where we track the people across multiple rooms, so we can track them basically when they walk through the building. We can also label the activities that the people are doing. At the moment, we're able to do stand, walk, sit pretty accurately. But in the future, I think you can think about much more finer grade motions that you're interested in. And with that, the first part is you detect the presence of a person, where the person is. So once you train the system on the person, you can also detect if this is a known person or is this a new person that is basically entering the building. So this could be used for intruder detection. You can track activity, and this is, of course, especially if we think about, our aging society, a lot of people living by themselves, and what they do throughout the day is a very good indication, to predict if there is some maybe health issues. And if we are able to capture the signatures of falls, we can also use those motion sensors, the RF, as a fault detector. So that's really the vision where you could take this in a residential space. So it's actually pretty exciting, but there's a lot more research to be done so that this gets accurate enough that it's actually useful. And this is what this will look like in an indoor environment. So you have your apartment, your house. You have several access points that form a mesh network because you don't want to put in new cables. You get consistent gigabit connectivity, which, I think this is almost, I would say, infinite capacity that you have there, at least for the next maybe 10 years. And those access points will also allow you to have ambient intelligence, and they can sense activities of people, of objects in the space, even if they don't carry a device. If they do carry a device, we can accurately localize it as well. And we will have a lot of different household robots that will help us to, for example, clean the space and perform other tasks. And they will also benefit, first of all, from this reliable low latency, so the intelligence can be in the cloud. and they will also benefit from the sensor information directly that's coming from those access points. So that's our vision for where we will be going in the home. And this is like, in an industrial space. So using all this multisensory system, we will get an idea of the space itself. So we can actually create a digital twin and model of the space. So this is the first step, that we, for example, know what our space looks like. Then we can get temporal information. For example, what we use now is, for example, to get information about the RF signal, how that is evolving, but all kinds of environmental sensor information that we have, we can know how this evolves over time. So we can use this for HVAC systems to automate the buildings. We can get information about the state of objects, people, the space itself, using the sensors that we have in the space, but then also using the sensors that we, for example, put on people. So the vital signs, we can measure that in this way. We have our robots are equipped with sensors, so they can sense the environment, but they also have, of course, a lot of sensors that track the state of the robot itself. Temperature, noise, whatever you want to measure. So we put the state information there. Having now all this information, we can start to find anomalies, detect anomalies, and basically, for example, I already mentioned the example of detecting falls, but something is malfunctioning, there is a noise there that shouldn't be there, hasn't been there before. We can see, of course, when we talk about people, there is something wrong in the heart rate, or we see there's, for example, the CO2 level and so on is getting too high in the building and so on. So we need to turn up the air conditioning. And then we can start to predict, for example, the motion of people. We can predict the evolution of the state. And, and then we can start to simulate, if we do this intervention, what would happen? So we can use this digital twin to actually simulate outcomes. So not just track the state, but simulate outcomes and use that in how we run the building. Of course, robots, autonomous vehicles, drones will be super important. I think we will see many, many of those, millions and millions of those in the next 10, 15, 20 years. And the same thing for people. So we will see them more and more being equipped with sensors. I already have my Oura Ring that tracks my sleep, and I cannot tell you how interesting and important insights I get from that. It was really helping me. And the same thing, happens with other, especially when we go to workplace safety. With the pandemic, we want to know if people wear a mask, for example. Do they adhere to the social distancing stuff? So I think it really helps us to augment people to make our workplace more productive and safer. And so this is a key enabler. We had this vision of that we can create this universal map that contains all this information. I think today I would call it a digital twin. And I think that's the term that's used today. And having this digital twin of the space, of everything that's inside, this is actually where we come then we came to the realization that actually where this leads to is that we create a mirror world. So we basically, in real time, digitize the physical world, everything that's in there, combine it with the digital information that we have. We create a digital twin, a model of this, and we think this will be the first place where this will take place is in industrial automation. So with this digital mirror realities, with these digital twins of the physical spaces, the processes, all our machines, all of our people in there, we can unleash a productivity that we haven't seen before. And that is really where, that was 2 years ago, that was our 10-year vision, is like, this is where we want to go. All of our research should actually enable us to do this. And this is also one of the key things that 6G will be about. It's like, how do we enable this reality, this vision? And the two things that are really critical there is being proximal. So you need to sense where things happen. And secondly, we need a lot of progress in our AI system, sensor fusion, so that we can create something at some point which will be a perfect knowledge engine, a perfect knowledge base, with which we can really start to simulate actions, automate actions, and unleash a productivity that hasn't been there before. So this is really the future. This is the vision that we have. And with that, I want to end this seminar talk. So I thank you very much for your attention.
Thank you, Klaus, for a nice and interesting talk. So let's give a big thank. So Luke, you have a question, so you can ask directly.
Okie doke. So just to make sure I heard you correctly, you did say earlier that you kept track of and recorded multiple RF signals in an environment. And so I was curious, have you had any interference issues with the RF signals? And if so, how have you addressed those interference issues? Because there's a lot of devices in a given space, and I figure that should cause a lot of interference.
Yep, and especially when we talk about Wi-Fi for RF sensing, so that's, the interference is not just visible in terms of that the signal gets more noisy, but the interference is also visible in a sense that the channel access is delayed. So you don't have let's say, evenly spaced sensing. So you need to be able to deal with that. So the sampling is not even. So it's not. And that is, you need to do a lot of pre-processing of the signal. So my team has spent way more time and effort than they expected on this to get something meaningful out. Yep, fully agree.
Okie doke, thank you.
Other questions? So I have a couple of them too. So two things. First of all, first one is a comment. So when you say biological world, you meant more human world, right?
Right, yes. And
okay.
This is, of course, we are mostly interested in humans, but of course, when you are a farmer, you will put those sensors on your assets, your livestock. So in agriculture, I think I would say it's also the livestock, the animals. We are collaborating with a vertical farming, indoor farming company, and for them it's their plants. So we are working with them using mobile sensors, so drones, to basically inspect the plants and see how they are growing, how certain interventions are affecting the plants. So I would say but of course plants grow slower. So you don't need the real-time aspect is maybe not as important as with humans and with livestock, but still, biological world also includes other parts, and especially when we talk about things like, climate change, we talk about things like environmental impact of whatever, then I think we can take the biological world more broadly. So we will see many more applications than just humans.
Yeah, the reason I asked, actually, we deal with cyber physical human systems. So you have the physical and the cyber, digital, right? But the human side, at least we have some understanding of the human behavior modeling with the prospect theory, rationality, and all this kind of. But in the let's say livestock or other animals world, do we know how to model some of those behaviors or not? Except some of the things that we do in swarm optimization and colony optimization type of thing, right? So that was my point. That you are right. So even if you think of the COVID-19 right now, how it is mutating, right? The smart virus, but we may not have the understanding of that and plug in with the physical and the cyber interactions to improve the experience that you mentioned, right? The sense or whatever, right? So anything that you have in mind?
Yeah, I mean, this is, of course, I have a really good friend of mine who is in livestock tracking. And, that was basically when the foot and mouth disease was with the mad cow disease, actually, at that time. When that appeared, there was people realized that we need to track our cattle, because if such a pandemic would spread across all our livestock, basically, there's so much interactions actually already that we need to know where all the livestock has been, on which fields, in which facilities where they have been in contact with to stop the spread of such a pandemic. And these systems are in place for years and years now for cattle. And so they have been actually ahead of humans, and I think there's still a kind of little bit resistance from humans to be tracked in that fine granularity, which I find healthy. So I think it's okay, if I'm at work,
right.
I have cameras that track my safety and do wear the PPE equipment that I need for doing my job to keep it safe. But, when I'm out and about, I'm not sure if I want to be tracked with that level of detail.
So in this context, I'll ask one question, then leave to other people. Is your group also looking at the privacy aspects?
Yes. So Nokia is very committed to privacy, and this is like, not just because we are a European company. We used to be the #1 cell phone manufacturer, and we had already in the early 2000s we had these projects where we anticipated that you have all these sensors in the phones. You can location-based services. We knew that GPS will soon be integrated in phones. And so then we started actually with the university in Lausanne, so EPFL. We had a really successful project where we looked at privacy aspects. And that, I think, in terms of research, really sharpened our sense for the importance of that. And now, of course, with the GDPR, so that is the European privacy ruling,
right.
You basically, it needs to be one of the first thoughts. And especially when we talk about these systems, the possibility of those systems, we need to also look at the privacy, security, and all these aspects. I fully, this is one of the key things that we need to do this right. And
Rambo, do you have a question? So you can ask the question to the speaker.
Sure. Thank you for the seminar. I want to ask two questions. First, how sensors are attached to access points? I mean, are they connected through network, or are they mounted physically? And the second question is how the access point is commissioned, for example, a UAV to do a job for it.
So can you repeat the last part of the sentence? How the UAV is...
You said that UAVs equipped with cameras can be used to monitor the environment. How the access point could communicate with the UAV to say, for example, monitor the certain environment for me.
Oh, okay. Yep. So this is, of course, the first part of the question is the sensors in the access point attached to it or just wirelessly connected. And I think we will see all of that. So, I would say that if we look at the smartphones, we have some sensors that we want to have. We put in there because people use it frequently. There's a lot of applications that use those sensors. And typically they're also dirt cheap. They don't cost much. So we put them into the smartphone. We integrate them. We put them into the access point in the future. And, that has, of course, a lot of advantages because they are directly connected to the access point. They are connected to the same time synchronization that the access point has. So that means that it is, by default, it allows us with microsecond accuracy, for example, that we can correlate events, which is really hard if you have the sensors distributed and just wirelessly connected. Maybe you have a slot where you can put additional sensors in, simply like you put stuff here on the USB port because not everything that some people may need you want to integrate because it becomes too big, too expensive. And then the third thing is like in a smartphone where we have Wi-Fi and Bluetooth where we can connect to peripheral. So we have also other sensors that we can connect to because maybe that location is not good for those sensors and so on. Or, it's just so few of people who need that. I think it's still out there what will be used. And so that's my answer there. So you will see all three of those, I think. And the second question was the UAVs. So I do not think that the intelligence will be in the access point. The intelligence is somewhere in a service in the cloud that says like, I take all this sensor information, I have this digital twin of the space, there is something going on, and I just have too much uncertainty at this point, and this is actually important to, for example, should I turn up the heating, or, should I just check what's going on? Is this just an anomaly there? So I want to send a different sensor to check out what's going on there. Or I sense a motion, and, this looks like a fall, but I'm not convinced, or I'm not sure it is. So let's send, but I don't have line of sight to any of the cameras there in the infrastructure. So let's send a drone there to inspect this. And so the drones are automated in a sense that they get a command, is like, go to this place and check it out. And then the drone would go there, stream the camera information. Maybe the drone has some cloud intelligence that helps it to basically identify people, to look around, get closer to them, whatever it is, how you do this. But there is some intelligence there that will send the drone to those locations.
Very good. Johnny, you are next.
Oh, thanks, Dr. Das. Excellent talk, Dr. Doppler. So a follow-up question is that, so you mentioned that the AI in cloud. So how do you view the AI in edge device versus in the cloud for the real applications?
That is a very good question. And
yes.
Yeah, go ahead. You can ask the second question as well. Go ahead.
Oh, yeah. The second question is that just a simple, like on page 25 in your slides, you mentioned that the people will not carry the smartphone. So you have a study in the living room. So how you get the RF signal data for your analysis? So maybe I missed that. So thanks.
Right. Yep. So the first question is on AI, edge or cloud. And this is just, for example, in the space that we were using in Murray Hill, where we basically collected some of our measurements. If you want to have full coverage with cameras, you need something like 125 cameras in that space. And that's what we have there, because it's a research space. And you can imagine what the aggregate data rate of those cameras is if all of those cameras stream with ultra high definition all the time, and how many GPUs you need in that edge cloud to process that data. So what we do today is we actually do stream that data over our networks. So they are still wired. But what we do there is the first thing is that we have some filters there, some detectors, AI system, very simple ones that can, for example, detect that there is motion, there's people there. So we only use those cameras, we only analyze those camera streams when we sense that there's something interesting there. So there needs to be this, let's say 99% of the data is actually you're not interested in. So, and that is the first part. And today we do that in the cloud, but of course, once we have designed the system that we say, okay, we know now what we are interested in, how we do this. We have, for example, AI acceleration chips that are flexible enough that we can load new networks on there, do the inference. Then we will do more and more, I think, in the edge device. And then use the cloud only when we need it, because that's in terms of computing, the most expensive one. And it is basically an optimization problem. It's cost, and of course, your service is the main thing that doesn't help you if you optimize the cost and your service doesn't work anymore. But I think we will see more and more things going to the edge, just to simply, focus the important stuff in the cloud. And even, with hundreds and thousands of sensors, cameras, your network starts to become really expensive, which we of course like as a network vendor, but I think our customers will not go in that direction. So we should do research in how to reduce the load on the network. So that was the first answer. And then the second answer was like, how did we collect the RF data when those devices have not been connected? And I think I go back to that slide, and because that is also a very, very, very interesting question. And I think there is actually a way. And this is the slide that you're talking about. And what we have there, I think this was a TV. This was, I don't know what device this one was, and this was also a TV. And this is our access point. And the way I think the Wi-Fi sensing will work is that there will be a background short packets sent between those devices in regular intervals. So either you have an active communication to the TV, then I just use the signal that I get from the TV that the TV transmits to the access point and use that for sensing. But if the TV is not transmitting, if I don't have regular transmissions, I think you will have, it's in Wi-Fi, it's called non-data packages that you can trigger the TV to send to you. It's used for training the channel. And with those non-data packages, I can basically make sure that there is regular transmissions between those stations and the access point that I can then use for motion sensing. Does that answer your question, or?
So are you okay to take one more question?
Yeah, I'm fine.
Okay.
This is fun.
So okay, so Anfield, you are next. Hello, me?
Hello. Okay,
Yes.
good evening.
Yes, we can hear you.
Okay, thank you so much for the presentation. I'd like to know if this, because of course, in the latest, very soon we, just like you said, we'll be surrounded with a lot of sensors which will be radiating. So I want to ask if some of this radiation are detrimental to the health, to the human health.
So you are thinking about human health in terms of wireless transmissions, or so does the signal itself or other impacts?
Okay.
I think that's the question, the effect of radiation on the health, because too much exposure.
On the health. Yes, and this is of course a thing where you know, I'm taking out my scientist hat now, and I think we have quite a few studies in this area already, going back to 2G on the health impact, and that is why we have, for example, certain regulation that limits the transmit power of devices. And of course, all the wireless industry is very interested in kind of making sure that our systems are safe. So there is quite a bit of research in that space. I think personally, I think that there's a lot of misinformation about 5G because people don't really understand the system. And you know, what I know about millimeter wave, for example, is that it actually, the higher the frequency is, the less it penetrates the skin, the more it gets reflected. And so that means that for me, logically, actually, the health impact of 5G millimeter wave should be less than for other systems because it doesn't penetrate our body as much. And there is the limits to the transmit power that we have. And the second thing is that we use a lot of beamforming with 5G, and that kind of limits the area that is exposed to the signal. So I think also that the kind of energy that you will receive is getting less and less because we have more directed signals. I encourage people to do research on this, and you know, I think it's something that needs to be scientifically studied, and if there is new realizations, then we should update the safety standards, because I think all of us rely on wireless communication, and we all want it to be safe. Yep. There's never a definitive answer on this kind of questions.
So Klaus, your talk has created a lot of interesting questions, synergy. So Michael has another question. So if you don't mind, Michael, you are next.
Go ahead.
Hi, very interesting stuff. I'll try to make this brief. We had a similar research environment in which people were actually living in the homes. And we found that after installing quite a few devices, even though they were, for the most part, engineering students, anything that took a lot of effort to coordinate, in other words, multiple devices, they ignored, which really surprised us. So I'm wondering if you think the future of this is to try to educate people or make the systems, completely self-serving to where people are not required.
Yep. And that is exactly the reason why we started the labeling through cameras and try to get that to a level where you don't need a person. And this is, of course, if you look at companies like Google, Facebook, they have armies of people, 10,000 people. Amazon Echo, for example, 10,000 people. And I think personally, I think the majority of those people are spending their time labeling data. And this is, as you say, is like, you can afford this for such use cases where there's huge economic opportunity behind it. So I can tell you from our part, we spent maybe 95% of the effort actually in automating everything there. The device management, it's like we have automated system to roll out the software that we need because we update it frequently. If you do this manually by hand, if anything, it's like just labeling an experiment is like just naming it and putting the right metadata in. It's like it needs to be effortless. And so, yeah, you will spend 95% of the time on that automation and only the rest on the research. So this is also why we don't see as much public data sets in this space than in other areas. It's much easier to go on YouTube and have videos.
Great. Is there any other question? If not, let us thank Dr. Klaus Doppler one more time for an